All right, so some very basic overview Astro 101 levels where we're going to start. Couple types of black holes in the universe. We've got stellar black holes that are maybe like 1 to 100 solar masses. They form from massive dying stars. They're located in galaxies, pretty much wherever stars are. Maybe they also are in AGN disks. That's a whole nother project that I will not talk about today, but I will talk about it with you if you want later. And so these form usually in supernova, we think. And then there are supermassive black holes, which are somewhere between 1 million and 1 billion solar masses. They form via question marks. And as far as we know, they are located in the centers of massive galaxies. If they are located in other places, we are not certain about that because we have not found them there. And so you may wonder, what is this giant many order of magnitude gap in mass? Where are the intermediate mass black holes? Do they exist? If so, how do they form? Where are they? Can we detect them? Are they doing things? Or is there just some bizarre hole in black hole mass? Probably not. So intermediate mass black holes, I like them. Also, Astro 101 level, there's the main types of galaxies. We have ellipticals, we have spirals, we have dwarfs. And they have black holes. At least elliptical galaxies have black holes. Spiral galaxies, at least massive ones, have black holes. Thanks for that. Dwarf galaxies, do they have massive black holes? If you had asked us, 15 years ago, we would have been like, oh, there's like 2. So probably not. And now we're like, maybe dwarf galaxies do have supermassive black holes, or at least some of them seem to have evidence for that. But like, which some and why and what physical process determines whether a dwarf galaxy gets a black hole but another one doesn't? Great question. Let me know if you know the answer. I don't yet, but I'm looking at it. So intermediate mass black holes in dwarf galaxies, I'm interested in figuring out how do they get there? When do they get there? Why are they sometimes there and sometimes not? And specifically, are they the seeds, these IMBHs, are they the seeds to supermassive black holes in massive galaxies? Do they have something to do with how supermassive black holes form in the early universe, some sort of intermediate mass seed early on? But maybe these don't grow into supermassive black holes based on some environmental or other physical reason. And so this is an important question because we don't actually know how you build a supermassive black hole. They've pretty much erased their formation history. So we don't know if you build them with lots of little black holes or like a pretty big black hole and a whole bunch of gas, or like a little black hole and a whole bunch of gas, or some other thing. It could be any of these. There could be stars collapsing involved. There could be all sorts of stuff. But we don't know. When we see a supermassive black hole, we can't ask it, how did you get there? And it's gonna be like, oh, well, there were these stars this one time, and then they came together. No, they don't know. We can measure like their mass and their spin, but that's kind of all we got. But if we could find intermediate mass black holes that do not have as deep of a history because they have not gotten so big, maybe that can give us a hint as to how supermassive black holes formed. So there's 2 local places that we can look. One is in dwarf galaxies. We can look for AGN, so active accreting black holes. Here's an example of, it's a little hard to see right now, but RGG 118 is a very pretty dwarf spiral galaxy. It's got a nuclear star cluster, and there's a 50,000 solar mass-ish black hole in the center. Masses are hard to measure, but it's definitely not a lot bigger than that, and it can't be too much smaller than that. So within an order of magnitude, it's definitely in the intermediate mass range. So there's a lot of campaigns now to look for more dwarf AGN. Another place to look is off-nuclear halo sources. So this bright blue spot right here is in the halo of this edge-on galaxy, and it's called HLX1 because it is a hyperluminous X-ray source. So its X-ray luminosity is up to 10 to the 42 ergs per second, but it's in all the ways we've estimated the mass of this object, it is probably around 10 to the 4, 10 to the 5 solar masses in terms of black holes mass. So it's probably either a star cluster or a dwarf galaxy that hosted this massive black hole that is being stripped and being accreted onto this larger galaxy, and something has triggered an accretion event causing it to glow. And it does this cool periodic thing, like every year it bursts in X-rays. It's very cool. So it's another place to look for intermediate mass black holes. But look for is not quite what I do, because this is a theoretical place. And so of course I use simulations. So what I do is I try and simulate these things and then give observers clues to how to predict them. So I use, or how to find them. So I use the code Changa, and I have two suites of cosmological simulations that I'm going to talk about today. One of them is called the Marvelous Dwarfs, which are 4 zoom-in cosmological simulations that are just volumes filled with dwarfs. So we have named them after 4 female Marvel superheroes: Elektra, Captain Marvel, Rogue, and Storm. And this is one of the Storm galaxies right there. And so these are very high resolution, just piles and piles of dwarfs with no massive galaxies in these simulations. And then we have another set that are similar, but they have one large Milky Way-like galaxy and then an environment of dwarf galaxies. These we call the DC Justice League. So we have our Marvel and we have our DC. These are named after 4 female Supreme Court justices: Sandra, Ruth, Sonia, and Elena. So similar sets of simulations, but in the Justice League, we have some Milky Ways, and in the Marvelous Dwarfs, there are only dwarfs. And so in these simulations, we form galaxies, we form, some of them have black holes, and we're going to study them. Continuing where we left off. All right, so I talked about intermediate mass black holes. We're wondering how they form. One idea of how they form, which is the basis for how we form them in these simulations, is something called the direct collapse model, where we assume you have a cloud of gas at around 10 to the 4 Kelvin, and some very specific conditions need to be met. So this cloud needs to be collapsing very rapidly, so a high accretion rate. There must be a low fraction of heavy elements to prevent cooling and fragmentation. We need some low angular momentum so that you can put everything into a point instead of it forming a disk. We may need an ionizing radiation background to dissociate any molecular hydrogen, so we just have atomic hydrogen. And maybe some other things. This is a long list of like maybe this, maybe that. We don't actually know if any of this is true, but it all does kind of make sense in that if all of these things come together, you could actually have a cloud of gas that collapses giantly into one very large object with a mass of somewhere between 10 to the 4 and 10 to the 6 black holes or solar masses. This only works if you can prevent fragmentation, prevent disk formation, so that you have a very large Jeans mass. Does it happen? We don't know. It's one of the leading theories, though, for intermediate mass black hole formation in the early universe, and this is how we're going to proceed in our simulations.
So how low an angular momentum do you need? This always seems to be unlikely.
How low an angular momentum? You want me to quantify it?
Well, for cosmological initial conditions, how often do you get this low?
For the cosmological simulations that I am discussing, we cannot measure that level of angular momentum, and so we do not use it as a criterion for seed formation. We use collapsing, low metallicity, and low molecular hydrogen fraction as our conditions. And the angular momentum bit is ignored in here. So we do not use that as a criterion. We use a 50,000 solar mass starting mass, which is the mass of the gas particles in these simulations. One thing I want to highlight is that we have a subgrid model for dynamical friction in black holes. And so this is important because cosmological simulations cannot properly resolve actual dynamical friction as it happens in the universe, because the particle sizes are similar to that of the black holes. And so if you toss a black hole into just a halo and you watch it orbit and watch its orbit decay without any correction, use a bunch of different models, and over billions of years, maybe eventually it will find its way to the center. But the Chandrasekhar timescale is here, this black vertical line, and nowhere is that met. And so we add a subgrid model based on the Chandrasekhar formula. And when doing that, if we toss a black hole into a halo and watch its orbit decay, instead, it will then, at least for most of these models, it will then decay at the appropriate time scale. And so this is a really important thing to add in order to properly capture the dynamics of black holes in galaxies. We don't want to glue them to any particular point in a galaxy, because if there's a galaxy merger and there's a bunch of dynamical mess going on, we want to be able to follow that. And we want the black hole to be able to respond to the local potential. And so we want, but we also need to make sure black holes don't get artificially flung out of galaxies. So this is how we solve that problem. Yes?
Question, like, is Chandrasekhar formula valid in this environment always? Like, it's thought like for collisionless gas, right? Is that always valid even when you're in the center and you have like very like dense gas? Is that always valid at this velocity?
We actually don't use it with the gas. The diagonal friction is only with the stars and the dark matter, so it's only with the collisionless particles.
For dark matter, you don't see when it's just like some like mass that is there and is not doing anything.
Yeah, it's particle based, so it's live, but it doesn't interact with anything, like dark matter. All right. So we also have an accretion mechanism based on modified Bondi-Hoyle relation and some thermal feedback. And I can talk to y'all about more of these details later if you like. So I've got a demonstration here of what one of our simulations look like. This is Sandra. And the colors here are gas temperature. So the blue is cool and red is hot, green is medium. And so you can see there's a massive galaxy forming in the center here. There is a supermassive black hole in the center of this galaxy, but I want to highlight that in some of the surrounding smaller galaxies, there are also massive black holes that have formed. Some of them are going to, some of these dwarfs are going to merge with our Milky Way type galaxy. They'll be disrupted. Their black holes will end up wandering in the halo. Other dwarfs may merge with each other, and other dwarfs just kind of hang out and don't merge with anybody, just like dwarfs in our local group. And so we end up with a sort of local group-ish simulation or situation. I mean, there's no Andromeda, but otherwise we have so our sets of the Justice League galaxies all look more or less like this, where we have a massive disk galaxy with a neighborhood of dwarfs surrounding them.
And the white is stars or something?
Yeah, the whitest stars.
And the red, what temperature was that?
I'm not actually sure. Aside from hot, I don't know. I can check on the video. All right, so the black hole seeds in our simulations form very on in the universe and then they stop. So we've got a histogram of seed formation times and redshift on the top axis. And you can see that after about 500 million years or so, black hole formation is mostly done, except for this one right here that forms quite late. And this is due to the metallicity criterion. So once stars start forming and supernova go off, they pollute the ISM and you can't form any more black holes. And so in our simulations, seed formation is only a high redshift phenomenon. And the galaxies that the seeds form in are very, very small. So this is a distribution of the halo mass at the time that the seeds form. And the colors are broken down by the different simulations, but you can, the general distribution shows that there's a peak at between like 10 to the 8 and 10 to the 9 solar masses, which is consistent with direct collapse theoretical predictions. And also, I just want to highlight that these are really small. Like this is the halo mass, not a stellar mass. These are tiny, tiny, tiny galaxies that these black holes are forming in, which is something that you need to be able to simulate if you want to study dwarf galaxies with black holes in the local universe. You need to make sure you can form a massive black hole in a small galaxy. So it's important that we don't set a halo mass threshold. It's just the local conditions that determine the formation of the black holes. Is that a question back there?
Are you going to talk, do they form in all of them or roughly all of them or like
all of the dwarfs? I think my next slide is the occupation fraction. So we're good. Look at that. All right. So this is the redshift 0 occupation fraction. I've got it in terms of halo mass and in terms of stellar mass and even magnitudes if you're into that. And so the general trend you can see is that the more massive a dwarf galaxy is, the more likely it is to host a massive black hole. And the ones that are very small have a pretty small chance of hosting one. And this is consistent with the few observational constraints that there are, as well as a lot of other theoretical predictions as well. So here are a couple of pictures of our simulated dwarf galaxies that host black holes. Each one is shown face on and side on. And there's a little red cross that indicates the location of the black hole. And you may notice that in some cases, the red cross is not in the center of the galaxy. Can you all see that even from the back? Maybe you can't. Okay, you can. Good. There's even one case where it's like not even really in the galaxy. And so you might think, well, what is going on there? It turns out to be sort of common. And it also turns out to be observationally validated. So in 2020, Amy Rines published this paper of a study of radio VLA observations of a couple of dwarf galaxies. And in these 13 galaxies, she found a compact radio source consistent with a massive black hole, and about half of them are off center. So this one is off center, that one, that one, that one, and some of them are central. This is off center. So about 50% of these radio selected compact objects in dwarf galaxies are off center. Which is about the same fraction that I see in the Zoom simulations. So here, back to simulations, is the distribution of distance from the halo center of the black holes. And you can see there's a big peak here. So a bunch of them are in the center, but a bunch of them are also off center. And I want to remind everyone here that we do model dynamical friction. And so this is not just some n-body scattering artifact. This is actually real. And I will show you how it happens. So it is galaxy mergers that displace or that cause black holes to be off-center. Black holes form centrally in their galaxies, but there's a merger that displaces them. So each of these plots here are the black hole distance from galaxy center versus time, each for a different galaxy. They all start out at 0. And wherever the star is where there's some sort of galaxy merger, which causes it to be displaced. Yeah.
Can you define galaxy center?
Galaxy center is within 4 softening lengths of the center, which in these simulations is 0.7 kiloparsecs, I think.
Is that like center of mass? Center of density?
So to find the center, we use this iterative shrinking sphere on the center of mass process.
But if there's a merger ongoing, does it lock onto one of them, or does it?
If there's a merger and it's a mess, then it will probably end up locking onto one spot. I don't know how often that happens, but I'm sure it happens because things are messy. So you can see that often at the point where the star is when the line jumps up, and that's where a black hole becomes off center. And in general, it does not come back. It ends up just kind of wandering further and further away, or sometimes it starts to come back, but it doesn't quite get there. They all have a little bit different histories. Some of them have multiple mergers. So this one has a couple. So I can show you a little movie-ish of this, more of a flip book. So at a redshift of 4.8, there's a very small galaxy here, and I've cartooned the black hole over it so you can see where it is. And as I go forward to redshift 4, 3.8, it's just kind of hanging out. It's hard to tell, but there's a little fuzz right here. There's a friend coming, and the friend flew by. But there it is. Now you can get a pretty good picture of it. The friend is much larger. So remember, this is our host galaxy. It's really hard to see that there's a faint fuzz around it, but there is. And it's basically coming into a larger, but still dwarf galaxy. So they circle around each other for a little while. And at redshift 1.4, they finally coalesce, and now the black hole stays within the galaxy. The host is tidally shredded, and this is pretty much the situation until the present day. The black hole will wander around the outskirts of the galaxy, but it does not work its way to the center, and I'll explain why. So these situations are mostly due to mergers between tiny galaxies that host massive black holes and larger galaxies, which sometimes do and sometimes don't. Here's an example of a dwarf that hosts multiple black holes. So it has a stellar mass of 10 to the 9, and it's got a central black hole of 1 million solar masses and the outer black hole of 50,000 or so, which is the seed mass in the simulation. And it's about 3 kiloparsecs from the center. So we can have more than one. Okay, so dwarf black holes, it turns out, accrete very little, at least in these Zoom simulations. And so what this is a histogram of is the fraction of accreted mass or the total mass, or basically how much of the mass is made of gas versus how much is made of black hole seed and other black holes. So 0 would be no gas and 1 would be all gas. And you can see this giant peak at 0. So almost none of the black holes in these galaxies accrete very much gas at all. The highest is at about 13%, which is actually very interesting and important because this can actually give us a limit as to the original black hole seed mass. If we know that black holes in dwarfs or wandering black holes in more massive galaxies don't accrete very much, we can know that if we can figure out how to measure their mass, that can give us a limit as to the formation mass or the seed mass in the early universe, if they have no history that has then been erased by accretion. All right. Oh, yep.
So just wondering, technically, how do you identify a black hole? Do you just place a particle-like object with a lot of mass in your simulation? And in that case, how would you identify this gas has been created to the black hole in the simulation?
Okay, so the black holes form based on gas particles that meet the criteria of collapsing, zero metallicity, and low molecular hydrogen fraction. So they form self-consistently in the simulation based on the local gas properties, but usually in the centers of halos. And so then we use a modified Bondi-Hoyle formula to determine what the accretion rate should be.
I see. So every time step you track the formation, and the accretion rate of the black hole, and you actively tracking the mass.
Yes.
I see. Thanks.
Mm-hmm. Any other questions? Is that a question?
Brian is singing.
I can see Brian.
Okay, great. Thanks, Brian. Okay. So with accretion rate, low accretion rates come low luminosities if you're looking for AGN. So this plot of bolometric luminosity versus cosmic time, the star points are observations of AGN in dwarf galaxies. These are local, and these are over many redshifts. The circles are the luminosities from accretion of the black holes in our dwarf galaxies. At redshift 0, they're all quite a bit lower than those which are observed. And then what the black dots are is, well, if you trace them back in time, what is the maximum luminosity they ever got to ever? And it's still not very high. It's still orders of magnitude underneath what are observed. And so these dwarfs that host black holes are not AGN and were not AGN. However, I do want to point out that there are actual observed dwarf AGN, and this is a pretty small sample. So really, what we would like to do is use a much larger sample of simulated galaxies that host dwarf with black holes to see, well, if we look at hundreds of them instead of a handful, are there AGNs there? And so we do that using the Romulus simulation, which is a uniform volume, also run with Changa at slightly coarser resolution. It's a 25 megaparsec volume. You can check out Tremel 2017. Certified organic, free-range, locally grown supermassive black holes. This is the Romulus slide that everyone is supposed to show. So here you go. But it's pretty great. And there's hundreds of dwarf galaxies. Many of them have black holes. So what do? Are there AGN? Yes, there are. I encourage you to focus on the leftmost plot. There's a lot going on here. So this is the X-ray AGN luminosity versus the stellar mass. So we have 10 to the 8, 10 to the 10, so a good range of dwarf galaxies. The colored points are colored by the Eddington fraction. So all of these colored circles are dwarf hosting AGN that we see. And they're pretty comparable to observations. So the blue crosses are from Bierkals 2020, which are all local galaxies. The green crosses are from MESCO 2018, which are at higher redshift. So you can see that there's a pretty good overlapping cloud there. And so the Romulus age dwarfs AGN do match the local dwarf galaxy scaling relations. And they also match with X-ray luminosity versus star formation rate for those that are star forming. And then there's star formation versus stellar mass. But you'll notice that there are also a bunch of gray circles and a bunch of lower limit arrows, which is what all of this comb here is. And so there are actually a lot of undetected black holes in the simulations as well. So that's what these gray points are. And so the ones that are detectable fall on the local relations, and the ones that are not detectable are hidden. So how do you hide a black hole? Why are they hidden? So I want to show you the black hole mass versus stellar mass relation, which is shown here in a couple different ways. So here we've got the points are colored by the AGN luminosity. So orange being the brightest, pink being medium, and purple being kind of faint. And then gray being under 10 to the 39 ergs per second, which for X-rays is kind of the boundary between, like, we're pretty sure it's an AGN versus this might be an X-ray binary or some other X-ray object. And so we're not sure it's an AGN, we're not going to call it an AGN. Yeah.
What redshift is it at?
0.05, so local. Yeah. So you can see that the points fall on the local relation, but there's also a lot of gray points, which also tend to fall on the local relation, but they're gray because they are below 10 to the 39 ergs per second, meaning that if we had pointed our X-ray observatory at them, we would not say this is an AGN because it is not bright enough. Yes?
How do you know the masses of the observed black holes?
Of the observed black holes? That's a big question. For the most part, they use, if there's a broad H alpha line, they use that plus the virial estimates, or you can use the fundamental plane of radio and X-ray if you have both of those data, or there's a couple other ways that people estimate black hole masses, but there's definitely, it's definitely a dark art.
They don't use lensing, this kind of like strong lensing in the future or not? Like,
Strong lensing to do black hole
if you,
masses?
detect, like, if there is a black hole there, right? Maybe that's KA or not.
No, probably not.
So you don't have
Yeah.
sources.
Yeah.
Alpha goes to GM over C squared, so for these black hole masses, it's milliarc second.
Yeah. Yeah, we need a solar system sized interferometer, so you can work on that. Yeah, so not only does a faint AGN luminosity prevent us from seeing AGN dwarfs, but also there's background X-ray light as well from X-ray binaries, from just hot gas from star formation in a galaxy. And so what we did is actually what Ray Sharma did, who is the author of this paper, which has been submitted, is estimated the AGN or the X-ray background in each galaxy based on the star formation rate and some other factors. And when people identify an AGN, they say, all right, it's got to be usually at least 2 times above the background level. And so what these colored points here are is different amounts above the background level. So the teal is 5 being the strictest cut of are you going to see it above the background? Orange-ish being the level of 2, and red being the most liberal cut of just 1. And then you can see there's still a bunch of gray points. And so all of those points, they may even be luminous, but if the background luminosity is also so large because there's a lot of star formation going on in the galaxy, you wouldn't be able to see it then either. The bottom plots are for off-center black holes, which also exist in the Romulus simulations, not just the zooms. And so with these, you can see that they definitely, well, first of all, they're mostly gray, so you can't see them for luminosity and background reasons. Also, they're quite undermassive compared to the local scaling relations. So the central black holes tend to match the relations, but the off-center black holes, because they're off-center, they don't have the opportunity to experience large accretion events, and so they don't grow to match the relations. And so overall, Ray has estimated that about 74% of central black holes and 88% of off-center black holes are hidden, either due to low luminosity or due to contamination from the X-ray background. Lots of hidden black holes. All right, so how do we find out how black hole seeds form? How do we find these hidden black holes? Lisa is going to do a great job of it. Oh, did you have a question?
Just a quick question. So for the off-center ones, do they see that in the data as well, that the off-center ones can be less massive?
The off-center ones do not have mass measurements as of yet because there's only the radio data on them, and that isn't enough to give us a mass. And so stay tuned. Good question. I also want to know. All right. So Lisa is going to revolutionize how we think about intermediate mass black holes. It's going to launch in the mid-2030s. This is sort of a hard animation to see, but it's basically going to be a giant cartwheeling triangle following the Earth. It's huge. The arms are 2.5 million kilometers in separation, which is more than 5 times the Earth-Moon distance. It's so big. It's going to be great. And what is Lisa going to measure? Intermediate mass black holes. So what this figure is showing is the redshift versus total mass of 2 black holes merging together. And what the colors are is signal to noise that Lisa will detect these mergers with. So if you have 2 black holes that add up to 10 to the 6 merging at a redshift 4, the signal to noise will be 1,000, which is red here. You know what's really cool? This goes all the way up to a redshift of 20 at decent signal to noise. Look at all of these intermediate mass black hole mergers that could happen at times when we can't even see photons because of the opaque universe at that point. So we can get gravitational wave signals with decent signal to noise from these early times. Yes?
For such a black hole at such a high redshift, isn't it just the seed of those most massive, like supermassive black holes at high mass?
Well, at a redshift of 20, we don't know how big the most massive black holes will be.
I'm seeing the mass to be 10 to the 6. So do you mean you have 10 to the 6 black holes at redshift 20?
Well, we don't know. Maybe.
Oh, I mean just the sensitivity.
The sense, if there are, Lisa will detect it.
I see,
That's the point.
Okay.
You know how much time is that SNR? So which is the time of observation to get that?
Ooh, that I don't know. Katie, do you know?
Because like
Yeah, I would guess 4 years for the original lifetime.
The massive black hole is that if they are an amazing probe of GR in principle, right? Because to get those SNRs, typically you have to wait a lot of time. So if you have any offset and if you don't know your waveform quite well, right, you can actually lose the system quite soon, right? So if you require, like, let's say, years of observation to get those numbers.
Yeah, this is probably assuming a 4-year time baseline. Yeah, which is the minimum time, which hopefully it will be 10 years and not 4.
Yeah.
Crossing fingers.
6 years of data.
Yeah.
For sure.
Yeah. Yes.
Is there a physically motivated reason for capping it at the redshift of 20? Or I guess how far does that clock extend?
Oh, I don't know. I've only ever seen it go to 20. Maybe after that, people are just like, what? No way.
I see you have halo formation around that time. And before that, you don't even have structures or very small structures.
Yeah. I mean, you could maybe go up to 30.
Lighter, I mean.
Yeah. But if there's, I mean, if there's, well, okay. We can
I
talk
mean,
about it
the
later.
fact that we don't think there are going to be black holes at those redshifts does not mean we shouldn't look for them.
Well, Lisa will look whether we wanted to or not. We can't aim it. We can't point it. It's just going to find what it finds.
Yeah.
So I've added some black points to this plot. And these are mergers that occur in simulated dwarfs in both the Justice League and the Marvelous Dwarfs. So in dwarf galaxies, not with supermassive black holes of the larger galaxies. And so there are numerous points here. And this is cool because dwarfs may actually be the hosts to intermediate mass black hole mergers at redshifts of maybe 8 to 10-ish. Most of these happen between redshifts of between 0 and 12. And most of the mass ratios are between like 20% and 1 or so. Yeah.
You're saying dwarfs at the time or dwarfs redshift zero?
Dwarfs at the time. Yes, dwarfs at the time. So the mass ratios of the mergers are written here, 1 to 1, 1 to 5. I don't know if you can see them, but yes. And so you may ask, well, are these really going to merge? Because mergers in these simulations are really actually sort of magic. Because you can't, there's orders of magnitude of physics that have to be skipped when black holes in a cosmological simulation get close together. We just kind of go bloop, and then they merge. I mean, they have to be close together like for a while. They can't just whoosh past each other, but there's still, there's no gravitational waves. There's no three-body scattering, none of that. And so what one of my REU students did is used an analytical delay time calculation for these mergers, basically starting from where they are in the simulation, which is pretty close together, and then saying, all right, if dynamical friction does this, and if loss cone scattering does that, and gravitational waves do this, this and that being a bunch of calculations, will they actually merge? And she found that the ones that are purple stars, 4 of them, will actually merge in a pretty short time that added about 1 billion years or a little less onto their merger timescale based on when they went bloop in the simulation to when they would actually merge. This pink one here has a coalescence timescale of 30 gigayears, so we're not going to see that one. And the other ones were unresolved, mostly because their galaxies were too small for us to really robustly calculate the properties. So this paper has been submitted, and you can check it out on arXiv if you like. Some of these mergers can probably happen. And if these mergers do happen, they will be in the Lisa band. So this is a plot of the characteristic strain of Lisa versus gravitational wave frequency. Anything above this curved line is observable by Lisa. So as black holes in spiral and merge, get closer and closer together, they move into the Lisa band, and they coalesce, and then they drop off the universe, at least the gravitational wave universe. But they all will coalesce within the Lisa band. So if they do merge when Lisa is in the sky, then we will see it. All right, last slide is that I mentioned way in the beginning about halo objects and what they are like. And so you could have intermediate mass black holes wandering around in your halo. Sometimes they merge with the supermassive black hole in the center of a Milky Way type galaxy. And so if I look at all of the merging black holes in these simulations, including the massive galaxies, this is the distribution of the mass ratios of the mergers. There's this huge peak right here, and then this sort of crumbs over there. The most common mass ratio is 1 to 50, and which represents an intermediate mass black hole merging with the supermassive black hole of a Milky Way-like galaxy, which is pretty exciting. But also this is a problem because when people calculate waveforms of black hole mergers, they never calculate this mass ratio because it is hard. It is hard computationally. It's pretty okay to do like 1 to 1 up to 1 to 10, and it's pretty okay mathematically to do like 1 to 1,000, but anything in between is very computationally intensive. You can certainly do it, but to do it in a mass-produced level with within lots of different parameter space is very difficult. And so for those of you who do gravitational waveform calculations, I urge you to work towards making mass ratios like this more feasible, because LISA is probably going to detect these mergers. And when that happens, we need to know what they will look like so we can identify them and learn from them. So there is my plea. All right. Oh, and there's your reminder that this is our motivation. And now we are done. So here are some conclusions. I've been here for a really long time though, because we had that whole thing. So I'm not gonna, you can read them on your own. I'm gonna stop talking and answer any questions that you have. Thank you very much for being here and hanging out with me today.
Thank you, Jillian. Question? I'll watch on the chat. Oh, they can't hear me. For folks on Zoom, I will watch the chat if you have questions.
Okay, Glennis.
Just my naivete about this, is seeing a merger at Z of, how do you, can you measure the merger Z?
We can measure the merger Z. It comes out in the waveform and the waveform modeling. And so the magnitude of the, or the amplitude of the wave. Yeah. So once we get the waveform, the redshift, there's some degeneracies, but it's usually not too hard to figure out what redshift it's at. And they figured out how to do it with LIGO pretty well too. So. Yes, we could definitely tell 20 from 10. And the other awesome thing about LISA is that it can tell masses with excellent precision, like within a few %, as opposed to using like a broad H alpha line and getting it within an order of magnitude. You could actually get black hole masses to a few % with LISA, which is super exciting. Okay, David, and then Teo, and then people in the back.
So just want to make sure I understand your black hole formation criteria.
Mhm.
It seems like you've taken sort of, no, which is reasonable, but like maximally optimistic. Does
Mhm.
not use the egg momentum criterion.
Mhm.
So if most collapse regions have too much angular momentum to go right to black hole, then this is sort of the most optimistic for direct collapse.
You could say that, yes.
Yeah. So I mean, it's, and if things went the other route of forming massive stars
Mhm.
and then collapse with that, I mean, at the resolution of the simulation, is it really direct? You know, if you have lots of gas forming massive stars, they merge, they form black holes, and that gave you your black hole, would you distinguish those two at the level of?
At this level, no, we would not be able to distinguish them. And so if you have a whole bunch of stuff going on in a very compact region, whether it's collapsing gas or whether it's a very dense star cluster formation, which then collapses on itself, at this resolution, we cannot distinguish those. But ask me in a few years what I'm up to, and we can talk more about it.
And then I'll choose option B.
Yeah. All right, Matteo.
Yeah, Jillian, thank you so much. That was a great talk. And like David, I'm also interested in the subgrid modeling of how the formation happens, this black holes. So outside of rotation, I guess that turbulent pressure and eventually magnetic pressure are also important effects. So I was wondering if people have looked at, in the simulation, I guess you could trace the evolution of turbulence in your cosmological simulation and also magnetic field. Probably you don't have that, but in theory, have people done that? And do you see an effect of like shutting off the formation at a certain level of turbulence and magnetism?
Yeah, that is a great question. We haven't looked at that. We are actually, there's a student in McMaster who is working on, or no, wait, there's a student somewhere who is going to start working on a turbulent model of a turbulent subgrid model to some of our gas properties, and magnetic turbulence, we're not there yet. But yeah, right now we haven't been able to look at any of that, so we're on it though. Okay.
I think this.
Katie, help me.
Yeah, I think we go first.
You have a high optimal depth question.
Okay. Well, just a quick follow-up to David's question. I think a technical question. In practice, how much adjustment of your threshold condition for black hole formation was required to get a reasonable occupation number of black holes in a monthly way like galaxies?
Yeah, that's something that I've worked on for, I mean, since I was a graduate student of just trying to figure out how many black holes should be made in the early universe when we cannot count how many black holes there should be. It's pretty tricky. And so the Romulus simulation has been has had a very large parameter search in its inception. And so there's been a lot of they definitely looked at all of the different thresholds very carefully in order to determine what parameters to use. And then we've done the zooms based on what was found in the Romulus simulation. And as we're going to higher and higher resolution now, that we're finding that we need to actually tweak some of those. And so, or it's always a work in progress.
Yeah, Nico.
Thanks, Jillian, for the great talk. I was wondering, is it known why the DC justice simulations do not reproduce observational black holes in the local group from dwarfs?
Well,
Like
they do reproduce the local group because the local group doesn't have any visible dwarf AGN, and neither do we.
But locally show us that they're like below the observed.
You mean, is this what you're talking about, or?
But for the DC justice simulations.
Yeah. So yeah, where partly the argument is that it's a very small sample size. It's 12-ish dwarfs, and this is a few hundred dwarfs, and the percentages that are hidden are pretty high. And so it's possible that it's just a small sample size, but on the other hand, it could be what I was mentioning earlier with Chris's question is that as we get to higher and higher resolution, we're finding that maybe the parameters we're using in our simulation aren't as appropriate. And so we're doing a large parameter search now. And so maybe it could be due to that as well. And so ask me in a few years, maybe 1 year.
Okay, thank you.
Yeah.
Yeah, and then last.
Yeah, I have one nice question. So could you explain how the Lisa to help to differentiate different seeding models?
How what can help
How
differentiate?
Lisa help to differentiate?
Oh, how
different-
Lisa will help. Sure. So Lisa can help because Lisa will help us know what mass range the mergers happen at. And so different seeding models predict different seed masses. So direct collapse would produce mostly the heaviest. What David is mentioning about clusters that collapse on each other might be a little bit smaller, around 10 to the 3. If you're thinking about population 3 stars or something like that, it's more like 10 to the 2. And so the mass order of magnitude of mergers will be helpful, and also the frequency of mergers, because for example, population 3 star black holes would probably be much more common. Direct collapse black holes probably much more rare. And so just how many black holes merge within the history, and also at what redshift they're merging at, can give us a lot of clues as to what the seed formation models are. So I didn't go into detail about all of the different models, and so yeah, but that's how you would answer that question.
Thank you very much.
Yeah. Okay.
You mentioned it's a small sample, but presumably Lisa will be detecting the cosmological sample. So I'm wondering if it's plausible to extrapolate the information in your simulation box to the whole universe in the early.
That's something that we can do with Romulus for sure. And it's one of the many things on my list to do. So yes, it's possible.
Thanks.
I haven't done it today. I probably won't do it tomorrow. It's on the list.
Oh.